Here is the direct substitution property. If the f is a polynomial or a rational function and a is in the domain of the function f, then the limit of the function f of x as x goes to a is just equal to f of a. It's just like a direct substitution. If the a is in the domain of the function f, if it's polynomial or a rational function. Here is example 3. It says find the limit of this function. So here is the function. This is f of x. In this question or in this function, we can't find the limit by substituting x equal to 1, because f of 1 is undefined. It's just not in the domain. So we can't apply the quotient law because the limit of the denominator is equal to 0. Instead, we need to do some algebra to factor or find the factorization of the numerator as a difference of squares. So what we're gonna have is limit of this function x squared minus 1 over x minus 1 as x goes to 1. It's just equal to x minus 1 times x plus 1. Here's the difference of squares over x minus 1. And don't forget the limit here as x goes to 1. The numerator and the denominator have a common factor, which is x minus 1. When we take the limit as x approaches 1, we have x is not equal to 1, and so x minus 1 is not equal to 0. Therefore, we can cancel the common factor and then compute the limit by direct substitution as follows. So I can just cancel this out. Then I will have the limit of the function x plus 1, that what we got, as x goes to 1. And by direct substitution, we can have 1 plus 1, which is equal to 2. Here is the final answer. Okay, here is example 6. It says find the limit of the function square root of t squared plus 9 minus 3 over t squared. Here we can't apply the quotient rule directly because the limit of the denominator is equal to 0. So here we're gonna just multiply by the conjugate. What is the conjugate? It is just the opposite of the square root of t squared plus 9. And instead of the minus, we put it plus 3 over the same function. Here it is. So now we're gonna have the limit multiplying these two together. This will give us t squared plus 9, because the square root and the square root will cancel each other, minus 3 squared, which is a 9, over t squared times the square root of t squared plus 9 plus 3 as t goes to 0. Here is the 9 minus, here's a minus 9, so we can cancel these two. We're gonna have the limit of t squared over t squared times t squared plus 9 plus 3 as t is going to 0. Now we can cancel the t squared from the numerator and denominator, and this will give us the limit of the function, rational function actually, 1 over t squared plus 9 plus 3 as t is going to 0. So by direct substitution, since the 0 is in the domain of this function, we're gonna have 1 plus square root of 0 plus 9 plus 3. This will give us 1 over 3 plus 3, which is equal to 1 over 6. Here is the theorem that says that the limit of the function as x goes to a is equal to certain L if and only if limit of the function from the right and from the left is equal to each other, and it's an L. So here we have example 7. It says that shows the limit of the absolute value of x is equal to 0 as x goes to 0. Let's recall that the absolute value of x is just equal to x when x is positive and equal to minus x when x is negative. since the absolute value of x is equal to x for x is greater than 0, we have the limit of the absolute value as x goes to 0 from the right, because it's x greater than 0, it's just equal to the limit of x as x goes to 0 from the right, which is 0. And for x is less than 0, we have the absolute value is equal to minus x. So the limit of the absolute value of x as x goes to 0 from the left is equal to the limit of the function minus x as x goes to 0 from the left, which is equal to 0. Therefore, since the limit of the right and from the left of the 0 are the same, then we can conclude that the limit of the absolute value as x goes to 0 is just equal to 0. In example 8, it's asking to prove that the limit of the absolute value over x does not exist. Using the fact that the absolute value, as we just said that it's equal to x when x is positive and equal to minus x when x is negative, we have the limit of the function as x goes to 0 from the right is just equal to the limit of the function x over x, which is equal to 1. And here by the limit law, we can say that because it's just a constant, it's just equal to itself. And when x is less than 0 and negative, that means that x is going to 0 from the left. This is equal to the limit of the function minus x over x, which is equal to minus 1. And by limit law, it's just a constant. Therefore, the limit of minus 1 is just a minus 1. And because the limit from the right and from the left is not equal to each other, therefore, by the previous theorem, the limit of the function does not exist. Here we have a really important theorem, which is the squeeze theorem, which is sometimes called the sandwich theorem. It says that if the function g is squeezed between function f and function h near a, and if the function f and h have the same limit as x goes to a, then the function g is forced to have the same limit L as x goes to a. We can see this example. It says or asks, show that the limit of the function x squared times sine 1 over x is equal to 0. First, note that we can't distribute just the limit for x squared and for the sine 1 over x and just find the limit, because the limit of sine of 1 over x as x goes to 0 does not exist. Instead, we can apply the squeeze theorem. And so we need to find a function f smaller than g of x, which is, here's the g of x squared times sine 1 over x. So we need to find f and find h. Find the function g, which is smaller than, and function h was bigger than g, such that both f of x and h of x both approaches 0. So what we're gonna do, we know something, that the function sine is always lies between minus 1 and 1. So here is the function sine 1 over x. It always lies between 1 and minus 1. Any inequality remains true when multiplied by a positive number. And we know that x squared is a positive number for all x's. And so multiplying each side of the inequalities by x squared, we got sine 1 over x multiplied by x squared, and 1 times x squared, and minus 1 times x squared. And since we know that the limit of the function minus x squared and x squared both are equal to 0, so we're gonna take that f of x is equal to minus x squared and g of x is equal to x squared times sine 1 over x, and h of x is equal to x squared. So using the squeeze theorem, we can just find the limit of function f and function h, So the limit of function f, which is limit of minus x squared as x goes to 0, equal to 0. And this equal to limit h of x, which is the limit of x squared as x goes to 0, and they are both equal to 0. Therefore, the limit of the function g is forced to be equal to 0. And here is the final answer.